chemistry. So this is Chemistry Cat. Unfortunately, we only have one chemistry lecture, and so this is the only Chemistry Cat you're going to get. I am sorry that you have to live your life like that. But Google has plenty of them if you want to see more Chemistry Cat. Okay? If you ever take me for chemistry, you will see plenty of Chemistry Cat. There's even a Chemistry Cat trophy. So first of all, we have to talk about what is chemistry. If I turn that off, can everybody still see what they need to see? Looks like it's darkest back in that corner. Are you okay in the back there? Yeah. Okay. I noticed last week the video was completely washed out, so I went to a darker background. I think turning these lights off will help with that also. But if you can't see, seeing what's going on now is much more important than seeing what's going on in the video. So if we need light, let me know. Okay? So chemistry is study of both matter and energy. We're going to talk more about the matter portion of chemistry. So matter is going to be anything that takes up space and has mass. So mass is very similar to weight, although mass is slightly different than weight because weight involves gravity. If something is a form of energy, it is not matter. Something is either going to be matter or it's going to be energy. And neither but the two shall meet in the middle. Heat and light do not occupy space. Because they don't occupy space and have mass, they are not matter. They are forms of energy. Looking at this picture, name, let's say, two forms of matter in that picture. People? People? Air. Air. There's two right there. Obviously, the objects, anything that's an object that you're seeing is going to be matter. And then there's also the air that we assume is around all of these people, right? What are two types of energy that you see in this picture? Light. There's light. Heat. Where is the heat?
How people are dressed.
Right? And so the body heat, right? It's cold out probably, and so there's not a whole lot of heat in the air, and so they're dressed warmly in order to hold in their body heat.
From the vehicles.
Right. These are gasoline engines. You know they give off a lot of heat when you burn things. So there's just a lot of types of matter in here. Certainly didn't cover all of them. We certainly didn't cover all of the energy, kinetic, potential, and chemical, and all types of energy in this picture also. So we're going to come back to that matter. And all of the matter in the universe is made up of our elements. And an element is a substance that cannot be broken down any further and still maintain its properties. Even if you use a chemical reaction. So the way to think of it is the elements on our periodic table are the most simple building blocks available to you. It's like having a bunch of different shapes and sizes of Legos. You can break apart a Lego structure down into individual Legos, but you cannot break apart those Legos, right? They're very, very hard. All of the known elements are on the periodic table. This periodic table seems to be a little bit older, and so there aren't any down here. Some of the newer ones will have some here. Some of those actually haven't really been proven yet. We know that you can make an infinite number of elements. We'll talk about why, but essentially each element is different by the number of protons in the nucleus. If you jam another proton in there, you're going to make another element. So the elements that are known, that have been proven and have been seen by humans, go on the periodic table. Most of our body is made up of a small number of these elements. Carbon, hydrogen, nitrogen, oxygen, calcium, and phosphorus. Where do you think majority of the hydrogen and oxygen are?
Blood,
which is primarily made up of water. We know majority of our body weight is water, and water is just H2O, hydrogen and oxygen. Carbon, all of the organic molecules that we're going to talk about today, the DNA, the lipids, the proteins, there's a lot of carbon in those, and so that's where the carbon comes from. Those also have a lot of hydrogen and nitrogen. What about calcium and phosphorus? Where do you think majority of those are? Bones. Our bones are primarily calcium and phosphorus. And so that basic building block of an element is called an atom. And that atom is the smallest piece that you can break your element down into and have it still be that element. I can have a chunk of sodium, and if I break it in half, I have 2 pieces of sodium. If I break that in half, I get smaller and smaller and smaller pieces of sodium until I get down to 1 atom of sodium. If I were to break that sodium atom into pieces, all of a sudden it's not half of a sodium atom. They're the individual little pieces that go into making 1 atom, and we'll see what those are. So in this picture, this is copper wire, and if you were able to look at it at the molecular level, what you would see is copper atom versus next to copper atom, that's the copper atom, all lined up in a shape making that copper wire. And so the subatomic particles that make up an atom, some of them are in the center of the atom, called the nucleus. Others are outside the nucleus. So out here are the electrons. Electrons have a -1 charge. They fly around in little orbitals around the nucleus, and then in the center, in the nucleus, we have 2 different particles. We have protons, which are positively charged, and then there are neutrons, which have no charge. They are uncharged. So in general, an atom will have no net charge, which means that we have to have an equal number of electrons and protons. The neutrons serve no functional purpose to us in this class. They sit there, they make the atom heavier, but they don't affect its reactivity, they don't affect the charge, they just sit there. So this is a blown up picture of a nucleus. So in this nucleus we have red neutrons and blue protons. If we expand this even further, we see that there are 3 of the protons and 4 of the neutrons. The element that we're dealing with is dependent on the number of protons. The atomic number, it's hard to see on this one because it's small and it's dark, but each one has a number. 1, 2, 3, 4, 5, 6. That's the atomic number. That's also the number of protons in that element. And so if we looked at this nucleus and we wanted to figure out what element it was, all we have to do is count that there are 3 protons. Look up here and find element number 3, and that's lithium. So the element is determined by the number of protons. If I stuck another proton in that nucleus, all of a sudden there'd be 4, and it's no longer lithium. It's now beryllium. So we're saying each element has the same number of protons, and that is the atomic number. That's what we just talked about. So this is gold, off of the periodic table. How many protons are in an atom of gold? 79. Gold is atomic number 79. That means that an atom of gold has 79 protons. In addition to having the atomic number, there's also what's called the mass number. The mass number is the number of protons, which is on the periodic table, plus the number of neutrons. A proton and a neutron weigh almost the same. An electron weighs insignificantly small. It weighs an insignificantly small amount. So if you want to find the mass of an atom, you can ignore the electrons, Just add the protons to the neutrons. And that is going to give you the mass number. On the periodic table, it's usually going to be underneath the symbol. So hydrogen, this is 1.00794. Why that's not a round, why that's not an even number, not just 1, is beyond what we're going to cover today. That's the chemistry class topic. But essentially what it means is the average of all hydrogen atoms in the universe have that number. And if the average is not exactly 1, that means that there must be some hydrogen atoms that are not 1. There must be some that have more than 1 for the mass number. But the protons can't change, right? If you change the number of protons, all of a sudden it wouldn't be hydrogen anymore. So the only thing you can change the mass number of an element is the neutrons. If you want to find the neutrons, if you're given the mass number, all you have to do is subtract the protons. Remember, the mass number is our protons plus our neutrons. If you know the element, you automatically know the number of protons. And if you're given the mass number, the difference between them is going to be the neutrons. The different atoms of an element, they have different mass numbers, which means that they have different numbers of neutrons, are called isotopes. An isotope is an atom of an element that contains a specific number of neutrons. So there are isotopes of hydrogen which have a mass number of 1. And if the mass number is 1 and it has to have 1 proton, it means it has no neutrons. An isotope of hydrogen with a mass number of 2 will have 1 proton, 1 neutron. Mass number of 3, 1 proton, 2 neutrons. A lot of elements, most of them have a number of isotopes. And each isotope can have different properties. Particularly in medicine, we use the fact that isotopes are often radioactive. If they have extra neutrons, sometimes they'll want to get rid of them. And so they'll shoot them off in the form of radiation. So these are 3 forms of hydrogen. There's hydrogen 1, hydrogen 2, hydrogen 3. We're saying the name of the element and then the mass number. We have 1 proton, so the mass number is 1, hydrogen 1. A proton and a neutron, mass number is 2, hydrogen 2. And then hydrogen 3 with 2 neutrons. This mass isn't an actual mass. When I say hydrogen 1, hydrogen 2, hydrogen 3, it's not 3 grams, it's not 3 pounds, it's not 3 anything. All that allows us to do is to compare the mass of one atom to another. If I have 2 atoms, one has a mass number of 1, one has a mass number of 2, all I can actually say is the one that's 2 is twice as heavy as the one that has a mass of 1. Carbon generally is carbon 12, meaning it has a mass number of 12. Carbon atomic number is 6. So how many neutrons are in carbon 12? 6. They have to add up to 12. There's 6 protons, so there must also be 6 neutrons. So we can say that a carbon 12 atom is 12 times heavier than a hydrogen 1 atom. And we can't take that any further than that. Remember, this is not grams. In the end, what it comes down to is a proton or a neutron weighs what we call 1 AMU. It's atomic mass unit. And that has no connection whatsoever to the real world. So a carbon 12 atom was going to weigh 12 atomic mass units. We can take those atoms and we can stick them together. We can take 2 atoms of the same element. We can take 2 atoms of different elements. We can take as many different atoms of as many different elements as we want and combine them together. If you take multiple atoms, put them together, you have a molecule. So up here, we have a molecule made up of two atoms of the same element. When we draw them, if it's the same color and the same size, we assume it's the same element. Down here, we have another molecule where we have two of the red atoms, but there's also a black one in the middle. So this has two atoms in each molecule. This one has three, but they're both molecules. Molecule is a general term, does not apply to anything specific. If you have at least two atoms stuck together, it's going to be a molecule. And this says just bound together in a discrete arrangement. What a discrete arrangement means is it's in a permanent, always the same arrangement. And so here we have red, black, red. If you had red, red, black, that would be a different molecule. If we take a molecule, essentially what we then have is what we call a compound. A compound is a molecule where you have at least two different elements. If we have this molecule where it's two atoms of the same element, that is not a compound. That's still an element. It's a molecule of an element. Down here, we have two different elements bound together. So that is a compound. Over here is a picture of a compound called iron pyrite. It's a combination of iron and sulfur, and it looks like that. It is different than if you just took some iron and sulfur and mixed them together. Here, it's always going to be a combination of iron and sulfur in a specific number of each. And so we have 2 irons for every 3 sulfurs. Over here, you can combine as much sulfur and as much iron as you want. We say those are definite proportions in a compound. And the properties of that compound are most often going to be very different than any of the elements that went into it. So the melting point of this is going to be very different than the melting point of iron or sulfur. How reactive it is going to be very different. It's almost impossible to predict the properties of a compound simply based on what's going to go into it. Sand is a compound called silicon dioxide. It's silicon, Si, dioxide, because there are 2 oxygens. When we write these formulas, there are what we call subscripts. And so number 2 here is a subscript. And when you write a formula, every element has to have a subscript. Although if it's a 1, it's assumed and you don't write it. And so here, because there is no subscript number here, we know it's a 1. And so the actual formula for this is Si1O2. So looking at this, number 1 here, is that an element or a compound? Element. How do you know? Say it again?
There's only one capital letter.
Right? I like that. There's only one capital letter. So if there's multiple capital letters, that means you have 2 different elements, right? The simplest way to tell if something is an element or a compound is it up there. If it is on that periodic table, it is an element. If it's a combination of 2 things that are up there, that's not an element, that's a compound. If what you're looking at has its own box on the periodic table, it is an element. If it doesn't, it must be a compound. So what is water? It's a compound. It's hydrogen, which is number 1, and oxygen, which is over here, number 8. What about sodium chloride? Compound. Sodium and chlorine are different elements. put them together, you have a compound. What about copper? Copper is an element. Copper is, I think that's saying C. My eyes aren't very good. It's small in there. But I think that's copper right there. So copper is up there, so it is an element. Next, we're going to talk about mixtures. So that bowl that had iron and sulfur in it is a mixture. If you just take two different things and mix them together, but they're not actually bound together at the molecular level, it's a mixture. In our bodies, most of our mixtures are going to be in water, because the majority of our body is water. So we're going to talk about mixtures in terms of water. And there's three types. There are suspensions, colloidal suspensions, and solutions. And essentially the difference between them comes down to how small the particles are. So a suspension is this. This is just a beaker with water, and then there's something that is suspended in the water. They're big pieces, you can see them, and if you let that sit there, it would settle out. The particles would either sink to the bottom or float to the top. One of the two. That is a suspension. Sandy water, sand in a water bottle, if you shake it up, that's a suspension. If you go to the lake and you take a sample, there's probably going to be little pieces of stuff in there. That's going to be a suspension. I'm giving them another example of a suspension. Something that you would have to drink with breakfast. Orange juice. What type of orange juice specifically would be considered a suspension? Because there's orange juice that would not. With pulp. If there is pulp, that is a suspension. You have to shake it, right? The pulp settles out. But if you have orange juice with no pulp, there's no particles in there that are going to settle. And so that is not a suspension. What that is a solution. A solution has very, 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 very small particles. They're so small that you can't see them. It's going to be completely transparent. It can have color, but it has to be transparent. If you had Kool-Aid, there's color there, right? But as long as you stir it up well, there are no particles floating around in there. If you let that Kool-Aid sit there, nothing's going to settle out. The sugar, the flavor, the color, they are dissolved in the water. That is a solution. Yeah, go ahead.
You said OJ was a solution, but you also said solutions were transparent. Isn't OJ opaque?
Yes, trying to rationalize this. No one's ever called me on that before. Okay, got it.
Okay.
So, orange juice is not a great example of a solution, okay? Orange juice with pulp is a great example of a suspension. But, not only is it a solution, but orange juice without pulp is also a colloid. Okay? A colloid is somewhere in between the two. There are particles that are big enough to be seen, but they're not big enough to settle out. And so if we let this sit here, it's going to look the same. It's cloudy, but it will not settle out. This is cloudy and it will settle out. This is not cloudy, and then this is cloudy, but it will not settle. Does everybody understand suspension, solution, and the colloid is in the middle? Colloids are very rare. Okay? There aren't a whole lot of examples of them. Most things are going to be either a suspension or a solution.
Thank you, sir.
So in the solution, which is primarily what we are a big bag of solutions that walks around, right? And so there are different parts things that go into a solution. Number one, a solution is what we call a homogeneous mixture. Because it doesn't settle out, every part of that solution is exactly the same. If we take a sample from the top, it's going to be the same as a sample from the bottom, on the left and the right. Homo being one, genius, I don't know. The opposite of a homogeneous mixture is a heterogeneous mixture. Hetero being different, right? So a suspension would be a heterogeneous mixture. In that solution, there are two parts. Number one is the solute. The solute is the thing that's being dissolved. That is the thing that there's less of. The other part is the solvent. The solvent is the thing that's doing the dissolving. Usually, that's what there's more of. In our body, the solvent is water. We have no other solvents in our body. In our body, the solvent is water. Everything else that is dissolved in that water is going to be the solute. And another term is aqueous solution. So an aqueous solution is just a solution where the solvent is water, which is us. So in this picture, we're dropping some white crystals into this beaker of a clear liquid. Which of these two things is the solute? The crystals. The crystals are the solute, and the clear liquid is solvent. The crystals are going to get dissolved in this down here, which is presumably water. So solute, solvent. Holding these molecules together are bonds. And there are different types of bonds to hold different types of molecules together. In general, well, a chemical bond is a force that holds multiple atoms together in a molecule. Here we have a carbon dioxide molecule. There is something that's holding that oxygen to that carbon and that carbon to that oxygen. If there wasn't, the oxygens and carbons would just fly around on their own. But they don't. There's some sort of a glue holding them together, and that is a bond. We have ionic bonds and covalent bonds. An ionic bond is going to be present in an ionic compound. A covalent bond is present in a molecular compound. And so an ionic compound is a compound made up of ions. An ion has a charge. And so an example of an ionic compound is going to be sodium chloride. We've got sodium chloride. We're not going to do too much with ion charges in here, but this sodium ion has a positive charge. This chlorine or chloride ion has a negative charge. And we all know that opposites attract. If you have positive and negatively charged things, they attract each other together. That's what holds together an ionic compound. An ionic compound is going to have a positively charged atom, an ion, and then a negatively charged atom or ion, and that attraction between them is going to hold them together. If you're looking at a compound and you want to know whether it's held together by ionic bonds or covalent bonds, the easiest thing to do is to look and see if there is a metal in the compound. And metal is going to be on the left-hand side of the periodic table. So we're not going to deal with a whole lot of different examples. So for us, we can make a clean cut in the periodic table. So if you see something from here over, you see how there's kind of two sides. There's here, and then there's kind of connector bit in the middle. If you see something that's in the middle part or the left, that's be a metal. And if you have one of those metals in your compound, it's going to be an ionic compound. You will never, ever, 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 ever see a metal in a molecular compound with covalent bonds. Metals do not form covalent bonds. So those covalent bonds are present in molecular compounds. So a molecular compound is going to be a compound that does not have a metal. And so these covalent or molecular compounds are only going to be made up of elements on the right-hand side here. And so carbon dioxide is a molecular compound. Because carbon is here, oxygen is there. They're both on the right-hand side of the periodic table. In a covalent compound, you don't have those charges. And so there isn't a positive and a negative attraction going on to hold those together. In covalent bonds, what happens is they will share an electron. Essentially what happens is carbon says, I want more electrons. Oxygen says, well, I want to share mine. And so let's share them. And so they both kind of grab onto an electron between them, and then neither one wants to let go. Because if one lets go, then they lose that electron. And so they both hold on to an electron in the middle, and so now they're stuck together. Does that make sense between ionic and covalent? Ionic has charges that hold them together. And those charges come from the fact that an electron actually moves from one atom to another. If an electron moves from one to the other, all of a sudden these charges appear. Remember that an atom has protons in the nucleus and then electrons on the outside. Normally, if you pick an atom off that periodic table, it's going to have the same number of protons as electrons. And so it has no charge. Let's use hydrogen as an example. We take a hydrogen atom, there's going to be one proton and one electron. So overall, there is no charge. But if a chlorine atom comes along, chlorine has 17 protons, 17 electrons. They're both neutral. But hydrogen wants to lose its electron. Chlorine wants to gain one. We don't have to worry about why. But if hydrogen loses one, now it has 0 electrons and gives it to chlorine. We now have 18. There's now an imbalance in each. This has one more positive than negative. And so that has a positive charge now. This now has one more negative than positives. So now this has a negative. You have a positive and a negative, they attract. In an ionic bond, electrons are transferred. One gives electrons to the other one. These charges form, and the attraction comes into existence. In a covalent bond, hydrogen will not give an electron to something else. It will say, let's share an electron. And so they both grab onto their electron in the middle, and then neither one wants to leave. That's your covalent bond. Covalent bonds come in two different flavors themselves, though. There are polar covalent bonds and non-polar covalent bonds. A polar covalent bond means that that sharing of electrons is not equal. Each element has a different strength that it's able to pull on the electron that it's sharing. So if you have two different elements sharing an electron, one is going to pull harder. And if one pulls harder, the electron gets a little bit closer to that one. And so the electron is closer to one than the other. We say that's a polar bond, because the electron is closer to one end than the other. If you have two of the same element, they're both going to pull with the same strength. And so that electron stays right in the middle. The electron is in the middle. The two ends of the bond are the same. And so that is a non-polar. Easy way to tell whether a bond between two atoms is going to be polar or non-polar, are they the same element? If you have a carbon bonded to a carbon, it's two of the same element. What's that going to be? Non-polar. But if you have carbon to oxygen, we now have two different elements. If it's two different elements, one of them is going to pull harder. So this isn't going to be a polar bond. All you got to do is look, is a bond between two atoms of the same element. Next we have hydrogen bonding. And hydrogen bonding kind of uses the word bonding loosely. It kind of holds things together, but it is not on the same level as an ionic or covalent bond. It's kind of temporary. If you were to look at the boiling point of different compounds, if you had a table, you would start to see trends of what determines how high the boiling point of a compound is, but then you would notice exceptions. You would see something that you would think would have a very low boiling point, but it would have a very high boiling point in actuality. Water is a really good example of it. In general, smaller molecules have low boiling points. Big molecules have high boiling points. Water is very, very small, yet it has a high boiling point. Right? If you want to boil water, you have to get it pretty darn hot. But there are other things, like carbon dioxide, that are bigger than water, yet at room temperature, they've already boiled. They're gases, right, at room temperature. So what really causes that big difference for things like water is hydrogen bonding. Hydrogen bonding can only occur in molecules that contain hydrogen bound to nitrogen, oxygen, or fluorine. And so you're going to have an NH, OH, or FH bond. If you see a compound that contains NH, OH, or FH, hydrogen bonding is going to occur in that compound. What that does is it creates extra attraction between all of the different molecules of that substance. So here's some examples. So the simplest example is water. Water is hydrogen and oxygen only. So there are hydrogens bound to oxygens. So here is water. We have a big red oxygen and then two white hydrogens. What hydrogen bonding is it's essentially a sharing of a hydrogen. So here we have the oxygen on this water that's attracted to the hydrogen on that one. And the hydrogen on this one is attracted to the oxygen on that one. Yet at the same time, the oxygen of this one is attracted to the hydrogens on the other. And so what happens is these hydrogens actually kind of lift off a little bit and they kind of hover in the middle. So where a covalent bond is a sharing of electrons, a hydrogen bond can be thought of as the sharing of a hydrogen. But it's not as important to the molecules as sharing that electron. These water molecules will come apart. It's a lot easier to pull these two molecules apart than it is to pull the hydrogen from the oxygen. Same thing goes with any mixture of compounds that have these types of bonds. So here, this is ammonia in water. Ammonia is NH3. That's a nitrogen and 3 hydrogens. So that's the blue one in the center. And so the nitrogen is attracted to the hydrogen on a water, but the 3 hydrogens on the ammonia are attracted to the oxygens on water. So you get kind of this network of bonds. They aren't incredibly strong, but there's a lot of them. I mean, we have billions and billions of molecules in a small sample of water, and they all have these weak little bonds holding them together. So in the big picture, it really adds up. Ammonia by itself will hydrogen bond. Hydrogen fluoride, that's a hydrogen and a fluorine. So you can have hydrogen bonding. Here, this is hydrogen fluorine, hydrogen fluoride with itself. But you could take hydrogen fluoride, mix it with water or ammonia. You could have a combination of all 3. If you have nitrogen hydrogen, oxygen hydrogen, or fluorine hydrogen, you will have hydrogen bonding. This is what holds together our DNA. We'll talk more about our DNA next week, but you know that DNA is a double helix, right? There are 2 separate strands, and they have to come apart in order to be copied. So why do you think hydrogen bonds are used to hold together the 2 strands of our DNA?
They come apart easier.
They come apart easier than what?
The ionic and covalent
Right.
bond.
It's very difficult to pull apart an ionic or covalent bond. A hydrogen bond, though, is much weaker. And so you can pull it apart. A hydrogen bond is strong enough to hold it together, but when you actually apply some force to it to pull it apart, it's going to come apart. If you've taken any sort of biology before, you know that DNA nucleotides base pair in a certain way, right? A's come with T's, and C's come with G's. We'll talk more about that next week. But the reason that those pairs always happen is because different nucleotides have different numbers of hydrogen bonds that they can form. A and T are actually these 2 up here. Adenine and thymine can only form 2 hydrogen bonds, whereas cytosine and guanine can form 3. And so if you take an A and a C and put it together, they don't match up. Not only is there a different number, but the position of them, they're not going to line up. And so the hydrogen bonding is not going to happen. So that's why we're always going to have the CG and AT pairing. Okay. I apologize. The type of lecture that we have to have is just really scattered. If you look at the learning objectives, it goes boom, 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 and we don't have enough time to really go into depth of all of them. And so if you have trouble connecting one to the other, please let me know. Okay? We have time to go over questions that come up, although if I don't have any, I just got to keep going. Okay? Any questions so far? Okay. So if we have a chemical reaction is going to actually break those ionic and covalent bonds. If you want to break ionic or covalent bonds, you have to have a chemical reaction. And chemical reactions come in 2 forms in terms of energy. Every chemical reaction involves energy in addition to the atoms. You can either gain energy or you can lose energy. The first one we're going to talk about is either called an anabolic reaction, an endergonic reaction, or an endothermic reaction. In chemistry, we talk about endothermic. That's the term we use. In biology, a lot of times we use the term anabolic. Okay? And then there's a third one, endergonic that I think your book will sometimes throw in. These are all the same exact thing. These types of reactions generally are what we call synthesis reactions, meaning you are combining multiple small things to make a bigger thing. And when you do that, you normally store energy. So an anabolic or an endothermic reaction stores energy. Energy gets stored in those molecules as you make them. The opposite is a catabolic reaction. So you have anabolic versus catabolic, endothermic versus exothermic, and endergonic versus exergonic. Exo, exer, it's exiting. The energy is exiting the reaction. The reaction is losing energy. Usually, this means things are breaking down. A big molecule is breaking down into something smaller. It doesn't really make energy. There's a reason that makes is in quotation marks. Because the energy is there. We're not making or destroying energy. We're releasing energy. We're releasing it in the form, generally, of heat. An exo or catabolic reaction is going to feel hot, whereas an endothermic reaction is going to feel cold. Fire is the best example of an exothermic reaction. If you burn something, you're breaking it down, right? If you take a log and you burn it, you're taking all the complex molecules that are in that log and you're breaking it down into very simple things like carbon dioxide and water. You get a lot of heat out of that, though. Our body is designed to capture that energy. Yes, when we break down things, we generate heat. That's why we're warm-blooded, right? And the more we exercise, the warmer we get. But our body is able to catch some of that energy before it gets turned into heat, and we can use it to make things work. We have pumps in our body, we have muscles that need energy to do things. You can capture that energy. We break down things that we eat to get the energy out of them. This is a catabolic reaction. Catabolic is the breakdown of a big molecule to make smaller ones. So here we have a big complex molecule. It's going to break down and form a number of small molecules and give off energy. In a chemical reaction, this is what we call a yields arrow. We say this yields that. You can just read it as this goes into that. It turns into that on the right-hand side. So down at the bottom is an example of a catabolic reaction. We're going to talk more about this in depth next week, but this is what we call glycogen. Glycogen is essentially a bunch of glucose molecules stuck together. And so we have this big molecule. We want to break it down into glucose. If you take a big molecule and break it down into smaller parts, in general you're going to get energy out of it. And so if we take our glycogen, we react it with water, we get glucose, and then our body's going to take that glucose, combine it with something called ATP to get this glucose 6-phosphate. A phosphate on a molecule generally means it has extra energy. Okay? So what we did is we took this glucose molecule and we stuck a phosphate on it. And so what we ended up with, we took the glycogen, we broke it down, and now we have individual glucose molecules, which we kind of had to start with, but now it has the phosphate on it, which comes from the energy released from breaking all of these bonds. Yeah?
I think that H2O that's called hydrolysis, correct?
Yes. Yes. We'll come back to that term now. The opposite is anabolism or anabolic reaction. So this, we're going to take a number of small molecules, add energy to them to make the bigger one. So this is taking glucose in forming glycogen. So here, we already have glycogen. So glycogen is a big long string. We're going to imagine that there's already a big long string of glycogen over here, and we want to add one glucose onto the end of it. Okay? So this glucose has a couple of phosphates, these phosphorus with the oxygen, and then there is a uridine on here. This isn't too important to us at this point. We're going to take this, we're going to stick it on the end of glycogen. When we do that, we now have our glycogen with this on it, but our phosphates left. Remember, a phosphate sort of signifies energy. We no longer have that energy here. The energy went into the molecule. Okay, we took the glycogen, we added the glucose. This was a high energy glucose. When the glucose went onto the glycogen, it's now a low energy glucose. The extra energy that it lost is stored in this bond holding them together. So, anabolic reaction requires energy to make something big. Catabolic reaction takes big, breaks it down, and releases energy. If we eat a meal, we have a bunch of glucose in our blood. We just took in a bunch of energy, right? But we don't need that much energy right when we eat the meal, and so we're going to store it in the form of this glycogen. When these reactions happen, there are a number of things that will affect how quickly that reaction happens. Number one is temperature. For the most part, if you have a reaction and you heat it up, it's going to react faster. If you have a reaction and you cool it down, it's going to react slower. Also, we can change the concentration of our reactants. If we take two reactants, we mix them together, but they're low concentration, they're going to react slowly. If we have the same reactants, but they're very highly concentrated, we have more of each reactant mixed together, they're going to react more quickly. And finally, the surface area. Imagine that we have a block of metal, and we're going to drop it into a beaker of a liquid. And this chunk of metal is going to react with the liquid. They can only react if they're touching each other. And so the liquid and the metal only touch right on the border of the chunk. All of the metal in the middle of that chunk is stuck. It cannot touch the liquid on the outside, and so it can't react. But if we take this block, cut it in half, we're going to have more metal or solid touching the water. So more of it's going to react. And the smaller you make these pieces, the more contact you're going to have between the solid and the liquid, the faster it's going to react. Finally, we have the presence of a catalyst. This is the more complicated of the four. A catalyst is something that increases the rate of the reaction. And enzymes in our body, which we'll talk about again next week, are a great example of a catalyst. One of the enzymes in our body, particularly in our liver, is called catalase. Catalase is an enzyme that takes hydrogen peroxide, H2O2, and it breaks it apart. Hydrogen peroxide will, on its own, break apart. So if you go to the store and you buy a bottle of hydrogen peroxide, you put it in your medicine cabinet, 20 years later you come back to use it, it's not going to work because the hydrogen peroxide broke down. But it's a very slow process. If you take hydrogen peroxide and you put it in the presence of the enzyme catalase, it's going to happen very fast. So here we have bubbles forming. Hydrogen peroxide broke apart and formed gas. A catalyst will take a reaction that would happen anyways and makes it happen more quickly. And the reason it does that is because it lowers the amount of energy required to make that reaction happen. Every reaction has what we call the activation energy. It's this hump, okay? In this graph, on the bottom, we have time. So as time goes on, we're going from left to right. The y-axis is a measure of the amount of energy in that reaction. For the reaction to happen, every reaction has this hump that it has to get over. And the taller the hump, the harder it is to get over, and so the more slowly the reaction will happen. What a catalyst does is it takes that hump and it breaks it into two smaller humps. And so if you can get over the first one, you're already going to get over the second one. It's like a roller coaster, right? If you go up one hill and the second hill is shorter, there's nothing stopping you from going over that shorter one. But by breaking the big hill into two smaller ones, you didn't have to go up as far before you could fall. So a catalyst lowers the amount of energy needed to make that reaction happen. By doing that, it's going to let more molecules react at the same time. Okay. That's our first section. Questions about that? That is like 2 months worth of stuff in a chemistry class. If you have questions about this stuff, please, please, please ask me. Most of our other lectures are not so diverse as this one. This one is just all over the place. Okay? Is there anything you want to talk about again before we move on? I'm going to try turning one of these. Not that one. Is that okay? I see people falling asleep.
Is it on? Is if the little screen's on, does that mean it's on?
Yeah, it's on.
Oh.
So there's a red light on top.
Oh, okay.
This goes off to say battery. There's a
Oh.
red light on top. If the red light is blinking, or it's orange light, that means it's recording. So we will see, can you see it better with the light off versus on? I think this will probably be fine. It's kind of dark with none. So our next section is inorganic biochemistry. So biochemistry is going to be the chemistry in relation to our body. Inorganic means no carbon. Generally, this is going to be ionic compounds. The majority of our body is made up of water, and water is inorganic. Anything with a carbon in it is going to be organic. Anything without carbon is inorganic. And water seems very simple, but water is actually one of the weirdest molecules that we know of. It does a lot of crazy things that we're not going to cover in this class. But it also plays a lot of roles in our body. Water resists temperature changes very well. You have to put a lot of energy into water, to get it to change temperature. And when you try to cool it off, you have to take a lot of energy out of it to get it to change temperature. And so that allows water to keep our body temperature very close to what it wants to be. Water, because the liquid, is also present in our joints. It kind of makes a fluid in our joints that acts as a lubricant, that prevents bone from grinding on bone. Water will dissolve a lot of waste products in our body. And so if our kidneys get rid of water, they get rid of the waste product also. So the kidney doesn't have to have specific mechanisms to get rid of each individual thing that our body makes, as long as it can get rid of water, the other things will follow it with it.